All right, so I believe we left off right there? No. Yeah. We left off there. Remember last time we did our little experiment with the little egg beaters, right? We did that. So we need to continue. No, did we talk about specific heat capacity last time?
No. Yeah, we did.
Yeah, we did. So we talked about this. I think that's where we ended. We talked about water. Oh yeah, we ended there. Sorry, we ended right there. There. Shh. Calorimetry. That's what we're talking about. Calorimetry. This is kind of what a lot of our labs involve this thing called calorimetry. In fact, our next lab, this is our calculation. And this is the process of finding the energy in an object. Energy in an object. And it works by conservation of energy and that there is no net change in the energy. In other words, if I have a group of objects, I put them together, I have hot objects and cold objects. The warm objects will lose energy to the cold objects until they all reach thermal equilibrium. But the net change in the total energy is always going to be zero. In other words, some things gain, some things lose, but the total energy is always the same. All objects reach thermal equilibrium. And when we say thermal equilibrium, it means their final what are the same. Final what is the same? Keyword. Temperature. The final temperature is the same. So the idea here is that Q1 plus Q2 plus however many things are there, Q to the n is always going to equal 0. Some are positive, some are negative. Remember I said before with our formula, MC delta T, it's very important that you have the right final. It's always final minus the start temperature on that. This is how they get, those little, on the food package, how do they know how many calories it is? Well, they do something like this, something called like a bomb calorimeter, where they burn the food and that energy goes into the water. So the water heats up a certain amount. And however much the water heats up, that energy left the food and things like that. Like you're going to do a lab like that, in the next unit. Questions? Yes, ma'am.
Okay, well, this isn't about calorimetry, but the chocolates we're doing for the start here, I mean, we're going to get this, right?
No. The reason we do them because we don't ever get them like this.
Okay.
There's not enough time in the semester. If I tried to get you there, it would kill you. Because it goes too fast. Which leads us to thermal expansion and contraction. As we add or remove, as energy is added or removed from materials, molecules speed up and slow down. This causes the molecules to move farther or closer. In a material, like your table, right? They're all vibrating. Now, it means they have a certain amount of kinetic energy. If I put energy into the table, they get more kinetic energy, which means more movement. If I have more movement, am I going to stay the same distance apart? I mean, if you were going, if you had a bunch of people that were kind of moving back and forth, if they started moving back and forth a lot more, what's going to happen to their crowd? It's going to expand. And it happens. Also, if you slow down, your crowd is going to contract. Your table is going to contract. It's going to get smaller. Which is why you have things like this in a bridge or any structure. Any structure, you have to give it some place to expand and contract. Or just like if you took a paper clip and you take that paper clip and you go back and forth, back and forth, back and forth, back and forth. Eventually, what happens to the paper clip? Breaks. Well, same thing would happen to structures, bridges, and stuff like that. That if you didn't give it a place to expand, as it gets expanded and contracted, eventually, somewhere it's going to break. So we give it a spot. Sometimes it's just a line. I mean, if you look at the underpass of Woodside Road, you will notice that it looks something when you go under 280 on Woodside Road, you look at the bridge. It looks something like this, where one side is attached and the other side is kind of overhangs on the slip, and so this side is given some chance to move back and forth, which means that you have a gap, and the gap gets bigger or smaller depending on the season. Now, this time of year, is the gap going to be bigger this time of year or smaller? Bigger, because the bridge will contract. It makes the gap bigger in the winter. In the summer, when the bridge expands, it gets smaller. The gap gets smaller. Now, this type of gap is done so that it's a little less smoother. I mean, this one you hit the little bump, you get a bump. This one's a little, see, we still have the gap. And notice there's a pretty big gap here, right? At this end and this end. This is the gap. It's moved quite a bit. But because of the teeth, if you drove across this, is this going to be nice and smooth? Yeah. This is why they use that system. It allows them to put fewer expansion joints, but on that. So, but still, if I had something like the San Mateo Bridge. Now, San Mateo Bridge, for every, say, 1,000 meters, there's only 1 centimeter of, it only increases 1 centimeter, or say 0.1 centimeters per degree Celsius. In other words, when you have a change in degrees. So that means if you had a change of 10 degrees in a day, which in the summer, that's not bad. So in the summer in the morning, it's probably, maybe about, say, 65 degrees in the morning. It's 100 degrees in the afternoon. That's like 45 degrees. But just 10 degrees. That means from day to night, that would be 1 centimeter. 1 centimeter. But the San Mateo Bridge is about 10,000 meters long, which means just a 10-degree difference would give a 10 centimeter gap. It's about that far. Now that doesn't sound so much, but would you like to have to drive across that gap? No. And that's only for 10 degrees. What about 40 degrees? Could be even bigger. And this is just a ballpark figure. It's probably actually greater than this. This is why they put a lot of expansion joints. Do they get that whole 10 centimeters throughout the whole bridge? Yes. But if I put a lot of them, each one is only going a little bit. Each one is only going a little bit, which is why I put more in. Because we don't want to all have to drive the General Lee, right? Jumping across gaps on the San Mateo Bridge. On that. Now, the same thing happens on ships. Now, I have these two. These two basically are made out of bronze. They're made out of the same material. So notice, it just barely fits through. Barely fits through. Now, if I heat this up, the ball up, what's happening to the ball? It's going to expand, means it can't get through anymore. But if I heat them both together, apart. Now what does this tell us? It tells us, one, not only does the metal expand, but notice in this ring, what happened to the ring? It expanded. The area inside the ring also expanded. So remember, these two are made out of the same material, right? On the Missouri. Well, actually, we're going to go back. We're going to go to New Jersey. Sister ship to the Missouri. Now, when I first reported to Long Beach, which is where the ship was being renovated, I noticed in the storage yard there were these long cylindrical things. I thought they were shafts, propeller shafts, because there was a shipyard. I realized later they're actually gun barrels, battleship gun barrels. And they're probably longer than this room is. There's one gun barrel. Well, the New Jersey had a problem. She had a cracked gun barrel lining, which means they had to replace the gun barrel. It's about 1982, 83. Trouble is, no one had replaced the gun barrel on a battleship since like World War II. Most of these guys were dead. So they'd never done it. No one ever done it. I mean, they knew the theory, right? Now, in the front of a battleship, the turret, we're talking about the turret. So you have basically this, it's like this, 22 inches of steel on the front of the battleship. That's how thick the front, what's called the glacis, the front of the turret. and there's a hole, and the hole is just big enough for the barrel to go in. Okay, so it's just big enough because about a third of the gun is inside the turret. Okay, so they start in the morning, they have this great big crane, they attach the barrel, and they pull the old barrel out. No problem. They put the new barrel in, and they get it halfway in, and it gets stuck. Now this is Long Beach, right? LA. Summertime. Hot. Now as it got hot, the gun barrel is doing what? It's expanding. But then again, the hole in front of the turret is also doing what? It's also expanding as well. So in theory, just like my little thing there, it should get through. But is the barrel and the turret made out of the same kind of steel? No. Guess what expanded more? The barrel. So the barrel expanded to a point where it got stuck. And so you had all these guys standing there. It's like, what do we do? Can't put it in, can't pull it out. So the only thing they could do is they basically have it hanging from this great big crane. They just had to wait until evening when everything cooled off, because not only if you contract more when you get hot, you're also, or if you expand more when you get hot, you're also going to contract more when you get cold. So it contracted down. Yes, they could do it. Lesson learned: when should you replace these gun barrels? At night. Well, winter might not help either, but at night. And no one had to die. Don't laugh. Almost every single rule. I learned one thing about being in the military. If they had a rule for something, don't do this, someone, somewhere, sometime probably died. Well, no, it may be in a movie, but this is something you learn very quickly in the military. Unfortunately, most rules we had in the military about things, someone died for that rule. And so this was something they learned without someone dying, which is nice.
Are there a lot of rules?
Oh yeah. These are kind of common sense things. And like a fire extinguisher. CO2 fire extinguishers, you always put them on the ground. When you use a CO2 fire extinguisher, you keep it on the ground. Because as you shoot out the fire extinguisher, it develops a static electric charge that can get big enough to electrocute you. Little things. Things that are not in books. These are things that are not in books. All right, let's watch this little video. Oh, what was your question?
It was even if they're the same metals, does it depend on the mass?
No.
Like if one is more mass.
Even if they were the same metal, just like my other thing here, if it fit, they would both expand at the same rate. On that, it should fit regardless. I mean, if I have something that will fit through, it's going to keep fitting through. You know, steel is not. Remember, not all steel is the same. There's lots of different kinds of steel. That's why if you get ratings, if you look at steel, you buy steel, it'll have like a rating. It'll say how much, what's in it. You know, what are the impurities? Because steel is an alloy. You have to do things to iron to make steel. But they also add stuff into it. Like stainless steel, you add like chromium and all kinds. There's all kinds of stuff they add to steel to give it different strengths for different purposes and things like that. Right, Juan Carlos?
Eureka!
By the way, their order is not necessarily my order.
The story so far. When molecules escape from a liquid, they spread out in all directions to form a gas or vapor. This process is called evaporation, the change of state from a liquid to a gas. When gas molecules are cooled, they go slower and crowd together more densely to form a liquid. This process is called condensation, the change of state from a gas to a liquid. And now, expansion and contraction. If you blow a balloon only partly full of air and leave it in the sun, it will get quite a bit bigger. If you take another balloon and blow it up as hard as you can, and then leave this balloon in the sun, it will very likely burst. Why? Why do balloons get bigger and sometimes even burst if they get hot? Because the air in a balloon which is, of course, a gas, consists, like all gases, of molecules flying about in every direction. When you've got zillions of gas molecules doing this, they push quite hard against the inside of the balloon. That's why its skin is stretched so tight. When the sun makes the molecules hotter, they go faster, so they bounce harder and more often against the inside of the balloon. This pushes the balloon outwards and makes it bigger. Hot molecules take up more space than cold molecules. It's as if a lot of angry wasps were buzzing about inside the balloon. The hotter they become, the faster they buzz. And the further out they push the sides of the balloon. All of which boils down to saying that when a gas gets hot, it takes up more space. It expands. On the other hand, if you let a balloon get very cold, the reverse will happen. It will become quite a bit smaller. Because the colder the air molecules become, the slower they move. And the less they push against the inside of the balloon, which can now squeeze them into a smaller and smaller space. Cold molecules take up less space than hot molecules. The colder the wasps become, the slower they buzz, and the less room they occupy. In other words, when a gas gets cold, it contracts. Do solids and liquids also expand when they get hot and contract when they get cold? Well, you'll remember that if solids get hot enough, they melt into liquids. And the hotter liquids get, the more quickly they evaporate into gases. That's clear enough. But what's not so obvious is that before the change of state takes place, in fact, as soon as the solid or liquid starts to get warmer, it does begin to expand a very small amount. This is because the faster the molecules move, the further they pull apart from each other, both in a solid and in a liquid. That's why a space is always left at the top of bottles to allow for expansion in case their liquid contents should become too warm. A bottle should never be filled to the top, in fact, because if the liquid inside it gets too hot, there's even a danger of the bottle exploding. Can you think of an everyday example of a solid expanding and contracting? Well, what do you think causes that ka-thump, ka-thump noise when a car drives over a bridge? It's the wheels running over the spaces that have to be left between the slabs of concrete in the road to allow for expansion in the summer and contraction in the winter. So now you know not only why cars go ka-thump, ka-thump on bridges, but also how to prevent bottles from exploding and balloons from bursting. Or do you?
All right. Now, because of specific heat and other factors, different materials, as we said, expand and contract at different rates. In fact, you have a very useful device in your house called a thermostat, and it uses what's called a bimetallic strip. This is a bimetallic strip. It has brass on one side and steel on the other. Now, brass will expand and contract at a much greater rate than steel, which causes the bar to bend. When you bend the brass, or the ice brass, it'll bend toward the brass because the brass is contracting more than the iron or the steel. Room temperature is straight, but if I heat it up, and it doesn't matter which side I heat up, the brass expands more. The brass will expand more, and it curls up. So the brass side is the part that expanded more on the inside. Now, as it cools down, it will then straighten out. It will straighten out on that. So we use these a lot in thermostats, like in your house. If you took the cover off the thermostat, now this is a very old thermostat. We usually don't use switches like this anymore. Now, in this particular thermostat, what you would notice is it looks like a spring. And it does act like a spring, but the spring is a bimetallic strip. So that as it heats up or cools down, the spring is going to get bigger and smaller. And what happens is this spring gets bigger and smaller. In this case, it would cause this little tube to tip over. And there's a little glob of mercury. We do not use switches like this. If you have a very old furnace or something, you might still have a mercury switch. But in this case, the mercury blob would go down. We have the contacts, and when the blob went over the contacts, it turns your heater on, or it might turn your air conditioner on. And then when it gets to the set temperature, it goes back again, and it does that. Now it kind of touches the contacts, so it makes connections on that. You see this in your like dryers, in your oven, and things like that. This is what regulates temperature. In fact, the circuit breakers in your house also use a bimetallic strip to trip them. The circuit breakers, when you're pulling too much current, too many electrons are going through there, that bimetallic strip heats up and it opens the circuit so your house doesn't burn out. It does the same thing that a fuse would do. A fuse would burn out, but in this case, it does use also a bimetallic strip is what makes a circuit breaker work on that. Which leads us to water. Again, we're back to water again. Water, another one of its unique qualities, and probably this is its most unique quality. Now, most substances, if it's a liquid, we cool it down. It's going to contract. It's going to contract, and it's going to keep contracting in a straight line as it goes to solid. It keeps doing that, keeps doing it all, and so it gets smaller, smaller volume as it gets colder. This is what Kelvin was looking at when he figured out there must be this absolute 0 point, because the volumes kept getting smaller, 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 and all went to 0 at the same point. But water above 4 degrees, it acts like all other substances. You put energy into it, it expands. You take energy out of it, it contracts until it gets to 4 degrees Celsius. Now remember, water freezes at 0. So at 4 degrees, it's still liquid. Notice at 4 degrees, as I'm still removing energy from it. Now remember, if I was adding energy, taking away energy, most other substances would continue to get smaller volume. But in water's case, notice the volume goes up. Goes up. So water is densest at 4 degrees. Now remember, why does the Missouri float? Because it's less dense than the water. Why does ice float, solid water float? Because it's less dense than the liquid water below it by a lot. Because even, I put an ice cube in something that's at room temperature, about 20 degrees Celsius. Does it sink to the bottom? It's still less dense. So in other words, we're talking that it gets pretty less dense on that. So, on this. So why does this happen? Well, it has to do with ice crystals. One, in most substances, when you go from liquid to solid, the molecules get closer. All right, they get closer together in their crystalline form. However, water, when it goes to its solid form and it forms that ice crystal, the molecules actually get much farther apart. Much, much farther apart. If we took this to scale, see how close the liquid water molecules are? Look how far they are away when you become the solid. This is unique for water. There's no other substance that does this. None. Because even if you look at the periodic tables, you learn something about the periodic table, compounds that go down a period. If I look at hydrogen fluoride, hydrogen chloride, hydrogen bromide, do they all have similar properties? Yeah, they're not exactly the same, but they have similar properties. If I looked at trihydrogen nitride, ammonia, hydride potassium, some of those elements are going to be the same. But if I go from dihydrogen oxide to dihydrogen sulfide, what can I say about the properties of water and hydrogen sulfide? Similar? No, not even close. Not even close. But hydrogen sulfide is that rotten out egg smell. That's what gives things that rotten egg smell, is hydrogen sulfide. But not even close. Hydrogen sulfide, solid hydrogen sulfide sinks in liquid hydrogen sulfide, like everything else. Water is the only thing that does this. So it happened, but why does that happen? Because when we get to 4 degrees Celsius, at 4 degrees Celsius, ice crystals start to form. Microscopic ice crystals. Can you see them? No. But because they're forming and they're pushing apart, what's going to happen to the volume of your water? It's going to get greater. Now, as you are melting ice, at 0 degrees is where you see no more solid ice. I mean, that's where all the solid ice disappears. There are still microscopic crystals. It's not until you get to 4 degrees that all those crystals are gone. That's why at 4 degrees, water is densest. This also means that's why our oceans don't freeze up. Because let's think about it. If water acted like all other substances, most of Lake Tahoe would be full of what? Ice. You might get a little bit of water on the very surface in the summer. But for the most part, most of Lake Tahoe, all 1,000-something feet of it, would be filled with ice. Because as soon as the ice formed, it would sink to the bottom. Many of our oceans would be frozen on the bottom to some extent on that. Although it's a little different because seawater is a little denser, and seawater ice, like if you went to the Arctic, can you eat the ice in the Arctic? Could you use it for fresh water? Yeah. Yeah, all that ice is fresh water. The process of forming ice actually forces the salt out of it. The crystal actually forces the salt out of it. So the ice, for the most part, when it gets really cold, is fresh water. Even the sea ice in the Arctic on that. But what does that do for us? Well, see what happens. Let's talk about Lake Tahoe. Now, one thing about deep water lakes, if you go to the bottom of a deep water lake, what's the temperature of a really deep lake like Lake Tahoe all year round?
30 degrees, 56.
Well, let's talk Celsius.
35. 4 degrees.
You go to the bottom of Lake Tahoe. You go to the bottom of Crater Lake, which is the deepest lake in North America. You can go to the bottom. You couldn't yourself, but you'd have taken submarines. But the bottom of a very deep lake is going to be at 4 degrees all year round. Now, lakes like the Great Lakes, probably not, because the Great Lakes, even though they're very large area-wise, they're not very deep. I think even Lake Superior is only like about 500 feet deep. I know, that sounds like a lot, doesn't it? But when you have a ship, you know, or like maybe in parts, I think when the Edmund Fitzgerald went down, which is the big ore carrier, I think where she went down was like in like 150 feet of water. It still sounds deep. You when the Edmund Fitzgerald, when the bow hit the ground, the stern was still in the air. It was still up above the water, you know, so that sort of thing. So, you know, relative things. I mean, I've actually gone swimming in water that was like 4 miles deep. Yeah, one of my guys lost his wedding ring in the water down there. He fell off his hand. He ain't recovering that. But what happens is, let's look at Lake Tahoe though. So here's Lake Tahoe, and in the summer, so here's the water. In the summer, the surface layer of the water gets kind of warmish. Notice I use that word warmish, because Lake Tahoe never really gets warm. Warmish. So say we're at about 10 degrees. Now these are all in Celsius. 10 degrees. But we're at the bottom of the lake. 10 degrees Celsius. 10 degrees Celsius, which is maybe about 50 degrees or so Fahrenheit. Room temperature is like 20. What we would consider room temperature is 20 degrees Celsius. 20 degrees Celsius. All right, so during the summer, now if you've ever been to Lake Tahoe in the summer, you get this nice surface layer. Okay, that's okay. And you dive down maybe about 15 feet, it gets really what? Really cold. Now, water is a poor conductor of heat, which means the heat does not penetrate very quickly down below. It takes all summer to get this like maybe 10-foot layer. Now, so you have 4 degrees in the bottom, 10 degrees on top. Now, winter comes. Winter comes. And so so now it's like minus 10 degrees on top. It's cold. I mean, even right now, even though they didn't have snow up in the Sierras, it was still cold. Keep in mind, cold does not equate to snow. They're not the same. So it's minus 10 degrees. So the air in contact, the air comes in contact, air energy goes to that. So this is going to go 10, 9, 8, 7, 6, 5, 4. Now the layer right below, though, the layer below is still at 10 degrees, basically, because it doesn't get too much things. So, but when this gets to 4, where does it go? Boom, to the bottom. That goes to the top. So we go to that 10, 9, 8, 7, 6, 5, 4, boom, goes to the bottom. Notice the surface temperature can't get below 4 until when? Well, what can we say about before we can get the surface temperature below 4 degrees Celsius, how much of the water in the lake has to be at 4 degrees? All of it. All of it. Now eventually, sometime in the winter, if it's a really bad winter, the top gets to 4 degrees. So now the entire lake is at 4 degrees. Entire lake's 4 degrees. Now, 3. But where does 3 degree water go? Does it sink? No, because it's less dense. Remember, the water right below it is 4 degrees. It doesn't sink. So now it can go 2, 1, 0, and freezes. For any lake to freeze, it first must get the entire lake to 4 degrees, which is also why does Lake Tahoe freeze over? No. Which tells you, does the entire lake ever get to 4 degrees? No. Oh, yeah. Good. You probably want to purify it, things like that. So as winter goes on, though, the ice is going to get thicker. So the ice, like here, our ice at the top will be about -10. The ice at the bottom is going to be at 0 because it's in contact with 0 degree water at the surface. And we go at the bottom still 4 degrees. So our fish is happy. Sluggish, but happy. And so depending on how long the winter is, depends on how thick it gets. Now, California lakes in general do not get, well, a lot of lakes do not get thick. Shallow lakes do. I think actually right now, if you went to Yosemite, well, maybe not right now because they'd probably be getting some snow. But up until this week when we start getting some rain, some of the areas that are usually closed in Yosemite were actually accessible. If you actually drive to them. There were some lakes actually in Yosemite that people were skating on that usually no one goes to because they're totally snowed in most years on that. But this is what happens. So the longer the winter it goes to 0 degrees. You go up like to Minnesota, a place like that, they play games like they put a car on the ice and you have to guess when the car's going to fall in the ice in the summer, in the springtime. Those you got to be careful after a certain point you don't go on the ice. Because up in the north, they drive on it. Those kids think enough that you can drive on the ice. Things like that. All right. Heat transfer. Okay, so that finishes that up. So we need to talk about our calculation for our lab next time. So let's write down this problem. In your notes. This is the calculation you will be doing for your lab next time. Write down this problem. This is basically, this problem is what you will be doing in lab. You are going to be finding the specific heat of an unknown metal. So let's write down this problem. We have a 5.5 kilogram sample of an unknown metal at 55 degrees Celsius. So its starting temperature is 55 degrees Celsius. And we are going to place it into 1.5 kilograms of water at 15 degrees Celsius. Which means as soon as I put that piece of metal in the water, where's heat energy going to go? It's going to leave the metal and go into the water. So the temperature of the metal is going to go down. The temperature of the water is going to go up until they reach thermal equilibrium at 25 degrees. So in other words, they both end at 25 degrees. This is the final temperature for both of these objects. And we want to know what is the specific heat of the unknown metal. So we can write down some things. So we have metal and we have water, or two things. Now we might have a third thing. You guys are in your lab are going to use this styrofoam cup. And the heat transfer to the styrofoam cup is negligible. So in our calculation, we are not going to have to worry about taking this into account. But other things, if I give you a beaker, a glass beaker, yes, you would probably have to take into account that the beaker is also getting some of the energy from the metal. But because we use a styrofoam cup, we don't have to worry about that. So there could be other terms. There could be a third or fourth term in here. So it's not just 2. We simplify it and just hold it to 2. So the mass of the metal, 5.5 kilograms. Mass of the water, 1.5 kilograms. All right? Start temperature of the metal is 55 degrees Celsius. Start temperature of our water is 15 degrees Celsius. The final for both is 25 degrees Celsius. Put it in the middle because it's the same for both. And they both reach equilibrium. Specific heat of water, of the metal, well that's our unknown. Specific heat of water is 4,187 joules per kilogram degree C because we are dealing with liquid water. Liquid water, we're doing it in kilograms. And our operating formula is always this. Q equals mc delta T. We just use this over and over and over again. All right. Questions? Everybody up with me? What? Q is heat. All right. So in this problem, the Q of the metal, the heat lost by the metal, plus the heat gained by the water is going to equal 0. As we said, this is, gentlemen, you need to step outside. Whatever energy is lost by the metal plus whatever energy gained by the water is going to equal 0. The sum is 0 because there is no net gain or loss of energy here. So we can say the mass of the metal, C of the metal, delta T of that metal, plus mass of the water, C of the water, delta T of the water, is going to equal 0. Now this whole thing, do we know the mass of the water, of the metal? Yes. Do we know the start and final temperature of the metal? Do we know the mass of the water? Do we know C of water? Do we know its delta T? So the only thing in all these letters I don't know is C. Basically this problem. Now, people like to get freaked out about this. This is the problem you're solving. That's what you're solving right there. In algebra, that's the problem you did. 2x plus 3 equals 0. Can you do 2x plus 3 equals 0 and find x? That's all this is. Okay? Once you put all the numbers in, you only have one unknown. Okay? So don't let all the letters freak you out. People like to see all these letters and they start freaking out. But in the end, you have all these numbers except for C. It's the only thing you don't have. It's this problem. That's all it is. So don't let it freak you out. Okay? Too many of you just, you see the letters and you just become overwhelmed. Okay? So, mass. So we have 5.5 kilograms times the C of the metal times 25 minus 55 degrees Celsius. Notice, final minus start. Because this is going to be a what kind of number? It's going to be a negative, because we're losing energy. Plus 1.5 kilograms times 4187 joules per kilogram degrees Celsius times 25 minus 15 degrees Celsius equals 0. I'll give you a chance to catch up. Remember, mass, specific heat of water. We know the specific heat capacity of water. 25 minus 55 here is 25 minus, there's a minus in there that got kind of gobbled up. 25 minus 15. Okay, so when I do this, I get C of metal times negative 165 kilogram degree C. Oh, thank you very much. All right, so C of the metal is negative 165 kilograms degree C. This is our units. Plus, well up here, kilograms cancel, degree C cancel, leaves me with joules. So I have 10, 25 minus 15 is 10, times 4, 187 times 1.5. And that gives me 62,805 joules equals 0. So notice, where am I? I'm at 2x plus 3. A number times an unknown plus a number equals 0. Are they big numbers? Yes. But they're still just numbers. Okay, that's why we have calculators. Now, yeah, so I get Cm times negative 165 kilograms degree C equals negative 62,805 joules, right? Because I subtracted from both sides. And you start looking at that, but negative, I mean, if mystery C can't be negative, I got a negative over there, but I got a negative over here too, and those negatives are going to cancel. So I divide both sides by negative 165 kilograms degree C. Now here, joules per kilogram degree Celsius, is that the unit for specific heat capacity? Yes, it is. So I have the right units, which that means I must be in the right place. So I get a specific heat capacity of 380.6 joules per kilogram degree Celsius. Just like that, which is, that's in the right ballpark. A couple of things. If you end up with a negative, you've done something wrong. C is always a positive. All right? So that's an indicator on that. Now, this is the calculation. You know, parts of this is what you would put in the sample. Basically, you have things like, you put in words, but you have symbols, numbers, and then your solution. That would be like your sample calculation. Stuff in the middle, where I work out every step, because some people need to see every step, some of you don't need to see every step. Okay, I just show every step. To be honest, it has to do with how, when I was in college, I had a professor who did not show every step and couldn't figure it out. To him, he went from here to there and said it was intuitively obvious, and it wasn't. But he couldn't explain how to go from here to here, because to him, he didn't need it. Not great. All right, questions on this? Well, now that you have a model, do this one. You should copy down this and solve it. So 10 kilogram rock at 100 degrees Celsius is placed in 20 kilograms of water at 20 degrees. If they reach equilibrium at 45 degrees, what is the specific heat capacity of the rock? So I'll give you like 10 minutes to solve this, and then I'm going to do it. You have 10 minutes to work together to solve this, and then I will on that. So I have 10 kilograms times C of our, actually it's a rock, isn't it? C of the rock times, was that 45 minus 120 degrees Celsius plus 20 kilograms times 4187 joules per kilogram degree Celsius times 45 minus 20 degrees Celsius, and that equals 0. So when I go through this, I get 10. 45 minus 120 is what, 55? So I have negative 550 kilograms degree C times C of the rock plus, so I have 25 times 4187 times 20 with, yes, negative 750. Thank you. Like that? All right, thank you. And then, so this comes out to be 2093500 joules, because kilograms cancel, degrees C cancel, leaving me with joules equals 0. Again, I subtract from both sides. C of the rock is going to be that negative 2,093,500 joules divided by a negative 750 kilograms degrees C. I skipped a step just for time's sake. So we divide by 750, and I got C of my rock of 2,791.3 joules per kilogram degree Celsius. What? 0.3, whatever. 0.3. I round to the nearest 10, 0.3. All right, questions? Good practice. This is the calculation. So I will not be going over that during the lab. This is the calculation you will do in your lab to solve the problem. Because basically you are going to try to identify your metal. By the way, one thing about metals, in this day and age, I can get basically almost any metal in any color. So although you will describe the color, all of you are going to have metal that's the same color. That doesn't mean you're all going to be given the same metal.